just opening this door as well, that might give a little bit of cross breeze, but maybe it has no effect at all.
It's good.
Excuse me, can I have your attention? If anybody didn't hear my announcement before, we have access to the 4th floor and the lobby in the 5th floor. So the lobby in the 5th floor is very large, lots of couches, places to plug your phones. You can go up there to have private conversation. And there's 2 restrooms on the 5th floor that you're also free to use. Okay, we can't use the hallways leading out of the lobby, but you can use the lobby. Okay.
Okay, so next we follow with Thomas Mixola, who talked about some pattern matching and DSLs.
Yeah, thank you very much. Yeah, thank you all for coming to this weirdly sounding talk, repurposing Scala's pattern matching for deeply embedded DSLs. What is it about? So DSLs. We would like to write our DSL programs similar to how we write Scala, including pattern matching. You can notice it's not exactly a Scala syntax, but close enough. But what we get is a reified representation, that is a data structure representing the program. And I don't mean the Scala AST. It's really the data structure that you design, that you have control over. And we're not going to use any macros either. We're not going to parse this as Scala. We're actually going to run this. And when this runs at the Scala level, it will be constructing our representation of DSL programs, including the pattern matching. So, no macros. By the way, if any of you heard of Scala-Virtualized, which was created some 10 years ago, you could do that with Scala-Virtualized, but that was a change in the compiler, in a branch, never made it to the mainline compiler. So we're going to emulate some bits of it by our own means without modifying the compiler, but we'll also differ in meaningful ways from what Scala-Virtualized did. You may be asking, like, why? Why would we want to do this? Maybe first, why do we need a reified representation if I have my my DSL embedded in Scala? Why not let it run as Scala code and do the thing that I would like the DSL to do? The answer is, I would like to have a freedom to add additional interpretation to my DSL code, not just run it as Scala, but, for example, serialize it, store it in a database, or visualize it graphically, or simulate it, like a dry run that does some logic but doesn't really launch the rockets or whatever. Then, okay, so if you want your own representation, why not just, why bother embedding it into Scala? Why not just write the parser for whatever language we want? And yes, you can do that, but it's not just the parser. You'll be writing type checker as well. You will want some tooling, maybe navigation in the IDE, autocomplete, and such. So it's not so cheap. So yeah, let's piggyback on Scala with what we can. Okay then, so aren't DSLs supposed to read like natural language? Why should we strive for the resemblance to Scala? Well, if you can do what you need with enough precision, with natural-looking language, good for you. But if you're going to need something like pattern matching, I think, well, if you have any ideas how to do it better, I welcome those ideas. But yeah, you need to have precision in the expression. And then you might be wondering what kind of DSLs would need pattern matching inside them, right? And we will see an example of that in a few minutes. So we'll be covering a few aspects of deeply embedded. Deeply embedded meaning that I really have a reified representation. But other than that, it applies to languages in general, not just DSLs. So we'll need a domain, sure, that will cover all the other aspects. Then syntax, that's the bit that we just saw, like how we write the programs. Then we need the intermediate representation, and this could be very close to syntax, but could also be distanced because we like to operate on some other data structures than directly the syntax tree. And then interpretation, of course, and as I mentioned, we could have many of them, like, of course, running, but visualization, serialization is also a different interpretation of the data structure. Maybe you want to compile it to machine code, maybe generate code for some other language, maybe do a dry run simulation, and so on. And these segments will mostly constitute the agenda today. First, I'll introduce the domain, then spend some time on representation, then the syntax that we saw, how would we translate it to the representation that we chose, and then interpretation will stay mostly out of scope, but I will have some comments about that. Okay, so introducing our domain of the domain-specific language. It's going to be workflows. If you are unfamiliar, here's a concise definition: a fault-oblivious stateful function that orchestrates activities. Okay, that's a mouthful. What's an activity? That's some business level operation, like typically calling some external service, and it can and typically does effects to an environment, so it's effectful, potentially non-deterministic. And then workflow is the glue on top of activities that builds the business logic from activities. The workflow is potentially, but maybe I should say typically, long-running, because either the activity could be long-running or it could be waiting for user input, for someone to click somewhere, gets an email and needs to click somewhere, so it could take days, weeks. And it should be resilient with respect to, okay, someone turns off the machine because the workflow runs for months, we cannot expect it to be in the memory for months. And also resilient with respect to intermittent failing activities, so it should do some retries. And the key feature, why it's interesting, why not just program this directly, is that you should get the resiliency out of the box without the designer of the workflow explicitly dealing with persisting the state. That should be provided by the framework or by the DSL implementation. An example workflow: employees in a company request equipment for Let's get some substrate for pattern matching, because I promised you pattern matching. So we are looking for an analog of enums. This is a Scala enum with two cases. Each of them has some data. Just a reminder, why not use such a data type in our DSL directly? Avoid contamination, as we just saw, but also we would need a Scala function to operate on Scala data type. So, and Scala functions are no-go for us. So we'll be aiming for something like this, or exactly this, where we define an enum just as a type alias that's composed of some bits, but has all the information that we need. And yes, even if you see strings here, this is completely type safe. So what are those underlying types? They are, as I just said, just uninhabited at Scala, but discernible one from the other, because they are different types but just don't have any values. And as I said, you should ask, what can you do with them? So what would you want to do with them? We will need to be able to construct them and then deconstruct them and handle each case, or handle it, consume it by handling each case. So we will want our functions, which are flows, to create, to get the input data and create the cases, or if I'm able to handle both cases, I say I'm able to handle the whole enum. Okay, how? Well, in our representation, just capture the intent, what you are trying to do. That's kind of true of any free data structure. So we're going to capture that, oh, I'm injecting this case into this larger enum, or I am handling all of the cases of this enum because I have provided handlers. Yeah, I will not go into details for this, but just know that it can be done in a completely type-safe way. So here, what we get is creating the for office case. Here, the flow is creating the work from home case. So this is just an example how it type checks that we get what we wanted. And don't worry, you will not be required to write this code or your user. Okay, and there's some evidence. You can reuse a data structure from a library that captures this in a type-safe manner. That really makes the invalid cases, because this is unknown, this is wrong label, unrepresentable. And this one is wrong because there should be this location here. Similar for handlers, same idea, just capture the intent, which will have a data structure that inside has handlers for each case, and anything else is unrepresentable by that representation. And again, this data structure is provided by the library. Okay, so but that will not be enough, because when you do pattern matching in your handler, you could reference variables from outside the match expression. So you will need to get those expressions into the right place, into the handler. And so you have handlers like this, where you have to have rise with your tuna or with your code. But it's not that you don't have rise, you have it, but the types don't align, because the handle primitive only takes enum as an argument, not enum and something on the side. So we cannot form the handlers. What to do about it? let's capture the intent again of distributing the rise to each of the cases, and then do handlers on the new enum, and these are the ones that we had on the side. Yeah, so this will be another primitive that you will have to provide, but don't worry, you can use a data structure from the library for that, and it does generalize to any number of cases in a type-safe way, but is somewhat involved. Okay, with that we have covered enough substrate to support pattern matching. So that concludes our representation segment. Now on to syntax. But maybe you are asking, okay, so why not just construct the program directly using these primitives? And the answer is because it doesn't look very nice. And yes, the font is small, but even if it's bigger, it's still unreadable. So don't need to read that. So could we get back to writing programs as we do in Scala, or similar, with variables, with lambda abstractions, with expressions? That is something like this for our use case. The input will be the request. We pattern match on the cases, whether it's for office or work from home. In the for office case, we are using nested pattern matching, actually. We match whether it's monitor or chair, and then dispatch it properly to the right department. So this is what we want. But how do we get from there to the representation that the kind of representation that we just saw? We didn't see the full one. And then from which we could generate this diagram. Let's break it down. I'll keep it brief. So we will look at what does flow do, what does switch do, and what do all these extractors that we are using here, what do they do? So what does flow do? Flow, see, it takes a Scala function, and it has to produce our representation, that is a domain function from request to result, that does not contain any Scala functions inside. So this might look like magic if you haven't seen this before, because how do I eliminate the Scala function? The trick is to not take a function from request to result. Those types are uninhabited anyways, request and result. We are taking some auxiliary expressions, and then I can remember with Scala function I can only run it, but we will be able to run this function by providing some prototype of an expression. So this is what the language designer has to do to support this syntax. And then use a library. Yes, this magic is from a library, but it's not quite magic. It calls a delambify method, which eliminates this Scala level lambda and creates our representation. Let's just in a minute or two look into how this works, just for an idea. So the library will have a representation of expressions, and yes, it will have variables in there, but only for a brief period of time. This will never be serialized. This will never get outside of your JVM, so even if you just do new object that's a unique variable, then we will need support forming pairs, accessing pairs, or each side of a pair, and if we have already an existing compiled flow, we can apply it to an expression. Lambda abstraction will not be needed because we immediately, when we encounter such function, we delambify it. Okay, so what does delambify do? Well, as I said, it manufactures a fresh variable and then can call the function that the user provided. This will give us an expression of b, which might look something like this. This only uses the primitive, the constructors of expression that we saw on the previous slide. These are mappings of mappings by an existing flow. Then there's forming pairs, and we can see this expression contains the variable that we created, but it may possibly contain some other variables from outer context. And then it takes this and eliminates the variables, gets to the point 3. I'll not go into the details, but the result will be this, where the second input is where the fresh variable will go, and it will still have to return, okay, I was not able to eliminate this I don't know about, but it's fed at this position, some expression sub3 that's using external variables. And if this is top level, if it returns you anything like this, you just fail, or if this is nested, you take it, okay, I will plug it to the outer flow. Okay, so that's how the magic works. It's not magic anymore. What do extractors do? So extractor will know. Yeah, this is a bit of boilerplate that the user will have to write to get that syntax that we saw. The extractor will basically have to know what type it is pattern matching on, and what are all the cases, and what is its case it is representing. So it will know all this information. Yes, the user will have to write an incantation, something like this, that's provided by you, the developer, the language developer, but you just instantiate a module from a library for your specific types, because the library does not know about your flow or your pair type or your enum. And then when this extractor is used, there's a bit of a trick. Notice, so this will be this is standard Scala syntax, an apply method. Notice that it always succeeds. That is as if it was total. Yeah, so we will need a representation that supports these non-total flows. But only for a moment. What does switch then do? Let's macro expand it to something where each case is separate, and then delambdify. We call the library which delambdifies each case. We'll have the extractors in each case, and then I'm out of time, so I will skip some bits here, but it will reorganize these cases so that they become completely exhaustive. If there was any unexhaustivity, it will report an error in embedded compile time, and then we lower to the representation that does no longer support those illegal states, those non-exhaustive pattern matches. Okay, so I know I skipped over this because I'm showed that I'm out of time, but yes, you can get a complete representation that does not support non-exhaustivity. That's this. Okay. So that concludes our representation, and as I said, I will not go into interpretation, just a few comments which are my final remarks, basically. That is, because we are in control of our representation, we can support durable execution, because at each stage when we start, but also during each step of execution, we have pure data. Partially applied workflow is pure data. So we don't need event sourcing to recover state. We just store it in a database. I showed you we can visualize such representations and visualize at any detail. You could make a visualization that's actually equivalent to the code. You could reconstruct enough to get everything. And visualize, of course, as it executes, because it's pure data. We didn't talk about concurrency, but if you are in control of your interpretation, you don't need the user to do anything special for concurrency. If there's something done in parallel, you can implement the concurrent by default execution. Same for cancellation. This is usually done on a level you are canceling threads or fibers or whatnot, but that's very error prone. If you control your representation, you can write an interpretation that whenever you don't need something anymore, you just chase it back up through the diagram and cancel whatever you find. Automatically, very safe. Workflows usually support some queries, like what's the state, or commands changing the state. And this is, I don't know why actually, done usually via mutating some state. And then when the workflow notices the change, it handles something. But this could be done as another input to your workflow of that would be some stream of requests or stream of commands, and then via concurrency and racing you would pick a command or do your stuff. So yeah, that's supportable. You could do templates of workflows. It would be just the workflow, just more parameterized, and then you can implement a partial application of workflow, and that would be instantiation of your template. You could simulate your workflow that is run, but don't run actually any activities. But when the result is needed, maybe ask the user interactively, what do you say was returned here? And if you go big, you can go full graphical designer and your own IDE with the migration path, as I mentioned before. But this would be just an alternative alternative representation to the Scala embedded syntax, and you could migrate your programs from there and load it up in your graphical designer. So the possibilities are endless if you are in control of your representation. So that concludes our agenda. And if you don't remember anything else, remember that if you are not in control of your representation, you are going to hit some hard limits on what you can do. So use a deep embedding with proper representation. And then if you are going to represent something like functions, there are multiple options, and some of them better than others at making illegal states unrepresentable. Even non-exhaustivity can be made unrepresentable. The code of this demo DSL is in the GitHub repo for Libretto, for the library we were using, and the equipment request example will land there soon as well. So feel free to have a look. I wish there was a version for accessible to dummies, but not yet. Be ready to roll up your sleeves, and I'll be happy to help you and take any questions.
So, okay, so
if we have time for questions, I guess we're kind of...
One or two questions, but very short question then, please. Because the food is already there.
There's a question, yes.
You mentioned Scala-Virtualized, virtualized, which is old and abandoned, but the closest thing in the current Scala ecosystem is the support for staging in Scala 3. Would it be possible, or would it have been possible to build what you're doing on top of that?
I would hope so, but I'm not sure. I'm afraid I would have to deal with Scala AST, which I don't do at all here. I just run Scala. So yeah, that's one thing I would like to avoid. And then, but one feature I would like from the Scala meta-programming facilities, as I was talking about, the errors are reported in embedded compile time, which is Scala's runtime, but compile time of my embedded DSL. Could we move that to Scala's compile time? And that would require evaluating at compile time any arbitrary expressions. That translation that we did, that moved, if we could move that to Scala compile time, that would be my wish, my favorite feature. And then regarding Scala-Virtualized, so yes, they were able to support the syntax, but they were not so opinionated about the representation, the point-free representation. So they will just give you like the expression representation with variables and there. So if something like Scala-Virtualized was in the mainline Scala, I would use that, but then still do my stuff for the translation to point-free. Making sense? Okay.
Thank you.
Thank you.